Welcome to Modern Physics. In this class, we will explore the experiments and theory that led physicists to abandon their comfortable ideas of classical physics and explore new ideas in relativity and quantum mechanics. So as a review, classical physics can be thought of as all physics that happened roughly before the beginning of the 20th century, so before about 1880 to 1900. Classical physics was roughly divided into mechanics, electricity and magnetism, and thermodynamics. So before about the 1880s, there were two known forces in nature, so gravity and electromagnetism. It was known that matter could be classified in the periodic table. So Mendeleev in 1869 came up with the periodic table of the elements. So this is an example of his early attempts at the periodic table. Exactly what the elements were, no one quite knew. So atoms were still a controversial topic in the 1800s. Some people thought that an atomic theory of matter provided a good description of some things, but there was not good evidence yet. And certainly no one knew anything about the substructure of atoms in the 1800s. In the 1860s, Maxwell unified electricity and magnetism to create his electromagnetic equations, and so these are sometimes called the Maxwell equations. So that had been developed, and then thermodynamics again was the field that explained gases and led to the ideas of heat engines and things like that. Okay, so classical physics was very productive. It produced a huge amount of devices in our lives. So starting with 1800, the electric battery was invented, steam locomotive, generators, motors. The telegraph and telephone were invented in the 1800s. The light bulb. The electric grid had just come into being in the 1880s. And then the automobile, this is a replica of one of the first automobiles created or invented in the 1880s. So there was like a motor on the back of this thing, and you could drive this little cart around. So classical physics, thermodynamics, all of these ideas had really shaped modern life. In fact, it was so successful that some people were thinking that all of physics had been figured out by the late 1800s. So Lord Kelvin supposedly said, "There's nothing new to be discovered in physics now. All that remains is more and more precise measurement." So they thought that all of the main theories had already been figured out. Classical physics was almost complete. The worldview of classical physics is the collection of ideas and assumptions that were just so embedded in physics that you didn't really even think about them, right? They were just kind of taken for granted. So one example is that the universe is deterministic. What does that mean? Well, it just means that the future state of the universe is determined by the current state. So for example, suppose we've got this box, it contains all these particles. If you knew the positions and momentums, masses of all those particles right now and how they interact, then you could do calculations using classical physics to predict where all those particles will be at any time in the future. So you can predict the future. So if you knew that, you could follow all of this dynamics. And of course, this is a computer simulation that does just that. From the initial state, the computer simulation takes all that information and makes a prediction of what the future state of the system is going to be. So under the classical worldview, the idea is that all of the universe is like this. In other words, our futures are already encoded into the present state of the universe right now. So That gives some issues with free will and things like that. And that is something that certainly philosophers were thinking about in the 1800s. Second assumption is that space and time are independent. So, for example, uh, you know, the assumption is that time flows at the same rate for everyone. So, if this person here has a clock, and a person riding a motorcycle has a clock, it doesn't matter what the velocity of this person is. The clock is going to tick at the same rate as a person who's just standing at rest. Another assumption is that mass is conserved, so mass can neither be created nor destroyed. So, for example, if you have, like, say, something is burning, so you have, like, wood that's burning, if you weighed the mass of the wood and the oxygen in the air and everything else you can imagine, and then you weighed the products of the combustion, like CO2, other gases that might be produced during the combustion. If you weighed all that up, it would be exactly the same before, during, and after, um, you know, the fire is going. So mass is conserved; it can neither be destroyed or created. Physical properties such as position, energy, and momentum are continuous variables. So, for example, if you had, like, imagine like a little ball that's spinning, or this could be the Earth. The idea is that if you could if you added a torque to this, you could speed this object up so it'd be spinning faster, or you could make it spin arbitrarily slowly. So you can the spinning momentum could have any value at all depending on the work that you do on it. Okay, so the final example is called local physical reality. So what that means is if you throw a ball upwards, it doesn't matter if anyone is watching the experiment. The ball will go up on its trajectory and then fall to the ground some moments later. All the physical properties that you can write down exist whether or not you are making measurements of those properties. Okay, so these seem like fairly reasonable assumptions, and I think all of these assumptions agree with our everyday experience of the world. But as Mark Twain says, it ain't what you don't know that gets you into trouble. It's what you know for sure that just ain't so. So, in other words, all of those assumptions of classical physics, we know for sure that all of those things are true. Except, of course, they're not. So, it turns out that we will see during this course that modern physics tells us that all of those assumptions are in fact false, in general. So there are experiments you can perform to show that that each one of those assumptions can be violated in different circumstances. And so we'll be looking at where these assumptions break down throughout this course. Okay, so modern physics can be broken into two different categories: relativity and quantum mechanics. So relativity can be further subdivided into special and general relativity. Special relativity applies to situations where things are moving close to the speed of light. General relativity applies near strong gravitational fields, like around black holes. Quantum mechanics applies when you're looking at things around the size of an atom or smaller. So our normal laws of classical physics work fine for our everyday life, but when you go into these extreme limits, we see that the laws of physics laid down by Newton and Hamilton and Maxwell start to break down on smaller and smaller scales, or near strong gravity, or when you get close to the speed of light. In those cases, you come up with new theories, and that's what this course is about. We can think about organizing these ideas into a little table here. So if if you're not moving close to the speed of light, and if you're looking at things that are not the size of an atom, those things are described by classical mechanics very well. Okay. If you start getting close to the speed of light, then you have to use relativistic mechanics. If you go down in size to atomic or subatomic scales, you need quantum physics. And if you're going really fast and really small, you need something called quantum field theory. So where does this come up in your classes at La Verne? So most classes that you'll be taking fall into the two left boxes. So physics 203 and 204, analytical mechanics, E&M, those classes all fall within classical mechanics. This class and quantum physics and solid state physics, astrophysics, those classes you need quantum mechanics for. Relativity really only shows up in this class and astrophysics, and then quantum field theory, you're going to have to wait for grad school if you're interested in quantum field theory. You need more advanced techniques in quantum physics before you can delve into that too much. Okay, so what is modern physics good for? Why study it? Well, fundamental knowledge is one reason. So if you want to understand the structure of atoms or solids or quantum optics systems, nuclear particle physics, that's when you would need modern physics. Also, technology is hugely dependent on the results of modern physics. So there's an estimate that over a third of the U.S. economy is based on modern physics, and that makes sense when you realize that all semiconducting technology is a result of modern physics. So, computer chips, solar panels, lasers, medical imaging technology, just a vast array of things in our everyday life are a result of modern physics. So there's lots of technical applications that come out of this. Okay, so this class will be broken into, we'll talk about relativity first, and then the second part of the class we'll talk about quantum physics. Okay, so hope you enjoy this class. There's lots of really interesting topics, and let's get going.